Hi guys, so today we're going to do lesson 5.2.1. We are going to review how to graph exponential and logarithmic functions. Alright, so go ahead, pause the video, try the warm-up on your own. This is a slight review of exponent rules, and then I want you to unpause it and double check to make sure you're doing it correctly. So obviously, as we're about to graph exponential functions, these are going to come up quite a bit, even just as we plug in values to the function. So it's really important that you guys remember exponent rules. So here, number one, we're dealing with a negative exponent on the outside. And the way that we get rid of negative exponents, first of all, we want to make them positive. We want all of our exponents to become positive, happy exponents, as I always say. And the way that we do that is by taking the reciprocal of the base. So if this in parentheses is the base and I take the reciprocal of that, the reciprocal is just going to flip-flop the numerator and denominator. So this will become y to the power of positive 4 over 7x to the power of negative 1. Now all of this to the power of positive 2. So we switch the numerator and denominator. Okay, next step is I'm going to use power rule. So I'm taking everything inside of the parentheses to the power of 2, which means I can multiply every single exponent on the inside of this by 2. And now notice how for the 7 I put a 1 there. If you don't see an exponent, the assumption is that it's raised to the power of positive 1. So I'm going to multiply 4 times 2, the 1 times 2, the negative 1 times 2. So I'd get y to the power of 8 all divided by 7 to the power of 2 times x to the power of negative 2. And then, again, I have another negative exponent here, so I'm going to see, okay, I want to move this x to the power of negative 2 up to the numerator. I'm going to leave the y to the power of 8 where it is and the 7 squared where it is because those are both positive exponents. So then I just carry this up here. I have the x squared now to positive 2 here. Okay, and then I can simplify the numerator. 7 squared I know is 49, and I'm just going to rearrange this to where it's x squared times y to the power of 8 because we typically like to write variables in alphabetical order, so I want to put the x first. Okay, number 2, similarly, we've got another negative exponent right here, so that's the first thing that I'm going to want to deal with. Since this is written as a whole number inside of the parentheses, I'm going to write this over 1, and then I'm going to take the reciprocal of it to make that a positive exponent. So this becomes 1 over 27 x to the power of 1/2 times y to the power of 6, all of this to the power of positive 1/3 now. Okay, and then I'm going to do the same thing that I just did in the previous example, so I'm going to raise every single value, every single term inside to the power of 1/3. So 1 is to the power of 1 technically. 27 is also to the power of 1. This is 1/2. This is 6. So I'm going to multiply every single exponent by that 1/3. So I get 1 to the power of 1/3 all divided by 27 to the power of 1/3 times x to the power of 1/2 times 1/3. So 1/2 times 1/3. I'm just going to do this over here. Multiply numerator times numerator, denominator times denominator, so 1/6. And then 6 times 1/3 right here. That's the same thing as 6 over 1 times 1/3. So multiply straight across, I get 6 over 3, which is 2. So y to the power of 2. Okay, now 1 to the power of any number is just 1. So 1, any number of times you're going to multiply it times itself gives you 1. And then when I have a fractional exponent, reminder, I can rewrite this as a radical symbol. So this becomes cube root of 27 times, same thing here, this is to the power of 1/6. So this becomes 6th root of x, oopsies, not y, x, times y squared. Okay, and then the cube root of 27, I'm looking for a number that multiplies times itself 3 times to get 27, so that would be 3. So 3 times the 6th root of x times y squared is our answer. And yes, it looks messy. We can't combine anything more, but we did simplify it quite a bit. So keep these rules in mind as we go forward and we start to graph exponential functions. Definitely you're going to be using negative exponents and plugging things in. Okay, so the basic definition of an exponential function is here. On the next slide, we will actually graph an exponential function, and then we'll talk about some more specific characteristics of these. So the most basic exponential function is written in the form of f of x, or y, equals some value b to the power of x. B is a positive constant meaning it is not changing. So it's not going to be a variable. For instance, we might have f of x equals 2 to the power of x, or f of x equals 7.5 to the power of x. Okay, so B is actually going to be some positive number other than 1. So it's not 1. The reason it's not 1 is because if it was, we'd have f of x equals 1 to the power of x. And 1, as we just talked about on the previous page or previous slide, 1 to the power of any number is just 1. And so that's actually a line. It's not an exponential. Okay, so b can't be 1, but it's going to be a positive number that is greater than 0. So b is greater than 0 and any number that's not 1. So it has to fit both of those descriptions. And then x, that variable, can be any real number. Okay, so let's look at a basic example. We've got f of x equals 3 to the power of x. Now, when in doubt, whenever you are graphing a new function or just one that you haven't seen in a while, you can always just make a t-table, pick some values for x, and then calculate the y value and graph it. So that's exactly what we're going to do here. I want you to make a table. We've got values for x between -2 and 1. So -2, -1, 0, and 1. We're going to plug those in here. So I'm going to start by plugging in -2 for x. Now you can do this over to the side, or you can just plug it directly into the other side of the table. So if I plug this in, I get 3 to the power of -2. That's where our negative exponent comes into play. So I'm going to flip this 3, take the reciprocal of the base, so it becomes 1 over 3 to the power of +2. And then 3 squared is 9. So I get 1/9, okay? And then I plug in -1, so 3 to the power of -1. Same thing, that negative exponent requires me to take the reciprocal of 3, so 1 over 3 to the power of +1, which is just 1/3. All right, then I plug in 0, 3 to the power of 0. You can double check this on your calculator if you've forgotten or don't remember, but any number to the power of 0 is 1, except for itself, okay? And then 1, 3 to the power of 1 equals 3. So we've got our table. We've got 4 points here. I'm going to go ahead and add these to the graph. So let's just add a couple values here. All right, so -2, 1/9. So -2, 1/9 is really, really tiny. It's really close to 0. -1, 1/3 is about like a third of the way up to 1, okay? So a tiny bit bigger than 1/9. 0, 1 is right here. And then 1, 3 is right here. So I'm going to connect these. You're going to notice that this is an upward facing increasing curve. So exponentials, we'll talk about this in a second, but exponential functions either look like this or they're going to be going the opposite direction where they're decreasing. So this is an example of exponential growth, which you guys are pretty familiar with, hopefully at this point, or you've seen this at least since Algebra 1. Okay, it's increasing exponentially is what we say. And then we are going to take a look at a second example here that's just a transformation of this, okay? So we've talked about transformations of functions quite a bit this semester, this year, but now if we take g of x and we say that that's equal to 3 to the power of x minus 1, I want to briefly remind you, okay, anytime we have an x minus h, that is the horizontal shift. And so this would be the horizontal shift. And then the plus k, if we had anything added on the outside of that whole thing, would be the vertical shift. Also, note or reminder that the horizontal shift, since it's a minus k, that's always opposite sign. versus the vertical shift is a plus k, so it's the same sign. Okay, so what this would tell us based on just this shift is that I can shift this. This is a -1, so opposite of that is to the right 1 unit. So for all of these point values, I'm just going to shift them to the right 1 unit. So this one, I'm going to draw this. This one would now be -1. comma 1/9, okay? And then it would be 0, 1/3, and then 1, 1, and then 2, 3. Okay, so it's just going to be shifted 1 to the right. So the nice thing about this is because we know transformations, once you know the general shape of an exponential function or a logarithmic function, the goal is that you can just utilize what you've learned about the transformations and the -h or the plus k value to then shift it. You're going to know the general shape, you're going to know the general characteristics, and the rest of it should be pretty simple. Granted, we can always still plug this in, okay? We could still plug in 3 to the power of -1 minus 1 if I wanted to plug this in here, which is 3 to the power of -2, which is 1 over 3 squared, which is 1/9. Okay, so we can always plug all those in and do it the old school style. However, this is just a lot simpler and easier if we recognize the transformations. Okay, so exponential functions, they are going to look very, very similar to this one here. Okay, what we also don't see on the graph, and I'll talk about this in a second, there is a horizontal asymptote right here at the x-axis, which is where y equals 0, okay? And so if you notice here what's happening in the table, every single time it's actually multiplying by 3, multiplying by 3, multiplying by 3 to get the next value, which is our multiplier here. Okay, that's the b value. And so if you undo that and go the opposite direction, you're dividing by 3 every single time. Well, when you divide by 3, even if you continue to divide 1/9 by 3, if you cut it into thirds, into another third, into another third, into another third, into another third, it's never actually going to end up being 0. It's going to be really infinitesimally small, but it's not going to ever actually end up at 0, okay? All right, so here are the main characteristics of exponential functions of this form, f of x equals b to the power of x. So the domain, if you look back here, the domain, how far does it go to the left and to the right? It's going to go forever and ever to the left and to the right. So the domain is all real numbers, okay? So all reals, or from -infinity to +infinity. The range is just 0 to infinity, not including 0. So notice here, because of the asymptote at y equals 0, it's just starting at 0 and it's going to go up to +infinity. So that's why it's parentheses at 0. It's never actually going to arrive at 0, and then it's going to go to +infinity. Okay, it's always going to pass through the point 0, 1 here if it doesn't have that shift, like this one has a shift, so that's just been shifted over 1. So instead of having the point at 0, 1 right here, now it's at 1, 1, okay? So that will have that point there. There's no x-intercept because it doesn't cross the x-axis. And then couple distinguishing things. So if the b value is greater than 1, which in this instance it was, this was a 3. That multiplier is a 3. So if that's greater than 1, then it's going to be an example of exponential growth, where as the graph goes to the right, it's going to be increasing. Okay, also the greater that the b value is, the steeper the increase. So if you have like f of x equals 100 to the power of x, that's going to be a really, really, really steep increase, because now you're multiplying every single term by 100 instead of just by 2. So the bigger the number for b, the steeper the increase. Now the opposite example here is if b is between 0 and 1, so it's still a positive number, but if it's between 0 and 1, meaning some sort of like decimal fraction between those two numbers, like 1/2 to the power of x, or 0.6 to the power of x, something along those lines, then the graph is going to be a decreasing exponential, okay? Because every time you're multiplying by each output by 1/2 or by 0.6, you're cutting it into fractions. So this would be an example of exponential decay versus growth up here. So it'll be decreasing. Okay, and the smaller the value, the steeper the decrease. All right, the other thing to note, we just talked about one-to-one functions. So exponentials, they are one-to-one, and it does have an inverse function. Its inverse is an actual function. We'll talk about that in a minute. Okay, and then again, I noted here that y equals 0 is the horizontal asymptote. The horizontal asymptote, that can change locations if there's a vertical shift. So if there's a vertical shift, then the horizontal asymptote will just shift with the entire thing. The horizontal asymptote, I'll say, shifts with the whole thing. Okay, so if I tacked on a +4 to this, all of these points would be moved up 4 units, including the horizontal asymptote. The horizontal asymptote then, instead of being at y equals 0, would be at y equals 4. Okay, so the horizontal asymptote is going to shift with the graph. All right, so those are the main characteristics of exponentials. Now let's define a logarithmic function. So a logarithmic function is actually the inverse of an exponential function. So on the previous slide when I talked about exponentials having an inverse function, well, that's what a logarithmic function is. It's the inverse of it. Okay, it's always going to be written in this form of y, or f of x, equals log base b. That's how we read this little subscript here. Notice it's a tiny bit below the log. Okay, so that's base b of x right here. All right, and so this is always going to be for where b is still greater than 0 and not equal to 1. So b has to still be positive and not equal to 1. And then x also needs to be greater than 0. That's how this is defined. Okay, so if x is not greater than 0, it's not going to work. We also we'll talk about this more next class, but the definition of a logarithmic function, because it's the inverse of an exponential, if you have an exponential y equals b to the power of some x value, to find the inverse, you switch the variables, right, x and y, so this becomes x equals b to the power of y. So this is where a logarithm comes from, okay? This statement here, this equation, is equivalent to this, and we'll talk about this more next class. For now, we're going to really just explore the graphs of logarithms. Okay, so in order to graph a logarithmic graph like g of x equals log base 3 of x, we first need to look at the graph of its inverse. So f of x equals 3 to the power of x. So notice how right here the bases are the same. So log base 3 of x is the inverse of f of x equals 3 to the power of x. Okay, exponential versus logarithm. All right, so we're going to use a t-table. We will calculate, just like we did for the first example, we'll calculate the table values for the original function, the exponential. Then we will switch the x and the y values in order to find the table values for the inverse, which is the logarithmic equation. All right, so f of x equals 3 to the power of x. We already went through this, but just as a reminder, if we plug these in, we'd get 3 to the power of -2, which is 1 over 3 squared, which is 1/9. Okay, the next one was 1/3. The next one was 1, and the next one was 3. So then, if we know that g of x equals log base 3 of x, so same base, if we know that this is the inverse, then all we have to do is we switch the x and the y values in our table for the original function, and then we can graph it. So we switch notice all of these x values right here are now these y values here, and then we do the same with the y values. So those become the x values, 1/9, 1/3, 1, and 3. Okay, so I'm going to graph f of x. Again, right here, -1, 1/3, 0, 1, 1, 3. Okay. And I'm going to label it. Please, please, please always label these functions. Even if you're using a different color, make sure that you are labeling. That way I can differentiate on your homework or on a test which function you're referring to. Okay, so now let's graph g of x in this separate color. So 1/9 is just like a teeny tiny bit away from 0. So 1/9 comma -2. 1/3 is a little bit closer way to 0. or from 0. So 1/3 comma -1, 1, 0, 3, comma 1. Now, obviously, we can graph a couple more points. I'd say the sweet spot for exponentials is really to graph at least 3 or 4 points, okay? And I'm going to label this g of x. So notice here, these look like inverses, okay? One thing to note is that when you're graphing an inverse, you graph over or reflect over the line y equals x, because your y and your x values, they all switch. Here's the line y equals x. Okay, so this should look like f of x has been flipped over this line of reflection, y equals x, because we've switched the y's and the x terms, and that gives you g of x, the logarithmic function, okay? So it's kind of a similar shape. Actually, it is the same shape. It's just been transformed. So it's still that curve, okay? And now it is increasing this way, upwards. And notice it's getting really, really close to the y-axis. So g of x, the logarithmic function here, actually has a vertical asymptote instead of a horizontal asymptote along the y-axis, which is at x equals 0. So these y's are getting really, 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 really close to that, but they're never going to cross that, okay? So the cool thing about inverses is not only do they switch coordinates, so the x's and the y's switch, but you'll see in a second when we describe the characteristics of a logarithmic function, the domain and range switch as well, and so do the asymptotes, okay? So we go from having an asymptote at y equals 0 to now x equals 0. All right, let's look at characteristics of log functions. So the domain now is opposite of an exponential. So the domain, if we look back here, the domain starts at 0, okay? It's not going to go further to the left. So it starts at 0, it's not going to actually touch 0, and it goes all the way to positive infinity. Versus beforehand, the domain was all real numbers. It could go as far to the left and to the right as it wanted to, but the range was restricted to 0 to infinity, okay? So then the range is from negative infinity to positive infinity. So the range is going to go all the way down forever and ever, all the way up forever and ever. So it's all reals for the range. So the range, domain and range just switch for exponentials and logarithms. All right, it's going to pass now through the point 1, 0 instead of 0, 1. So since that switched, okay, here, this passes through the point, and I know it doesn't look like it on the graph. This is passing through the point 0, 1. So now logarithmic functions are going to pass through the point 1, 0 unless they've been transformed. Okay, there's going to be no y-intercept. Just like for exponentials, there's no x-intercept. It never crosses the x-axis. This one is never going to cross the y-axis, so no y-intercept. All right, so same deal here. If b is greater than 1, which in this example it is, it's going to be increasing. And if the graph is decreasing, that's because the b value is between 0 and 1, like so, okay? So it'll just be flipped. And then x equals 0 is a vertical asymptote, just like I said right here. All right, so let's just practice a little bit more. We've got 2 more examples and then your homework. Okay, so f of x equals 4 to the power of x. So I am going to plug in these values here for x, okay? So 4 to the power of -2 gives me 1 over 4 to the power of positive 2. And then 4 squared is 16, so 1/16. 4 to the power of -1, so this gives me 1 over 4 to the power of positive 1, which is 1/4. 4 to the power of 0 is just 1. And then 4 to the power of 1 is 4. So we've got 1/16, 1/4, 1, and 4. I'm going to go ahead and graph these real fast. So -2 and then 1/16 is super close to 0. You're just approximating that. -1 and 1/4 is if we break this into fourths. Okay, 0, 1. It should go through that point again because it's not been transformed horizontally. And then 1, 4. All right, so here is f of x. Okay, and then g of x, we're just going to switch the x's and the y values. I don't even have to do work to plug these values in. So this will become 1/16, comma, -2, 1/4, comma, -1, 1, comma, 0, 4, comma, 1. So again, I'm just flip-flopping these. Okay, so 1/16 is super, super close to 0, comma, -2, 1/4, comma, -1, 1, comma, 0, and then 4, comma, 1. And make sure, I know mine looks awfully close to the y-axis. Make sure it's not actually crossing over there, okay? So this is g of x. And again, you can do kind of a quick visual check. Does it look like it's reflecting over the line y equals x? If it doesn't, then something probably went wrong. Okay, and then I would like for you guys to go ahead and try this. So pause the video on this one and sketch these two graphs for me. Okay, and then once you come back, we'll plug these in. So 2 to the power of -2 becomes 1 over 2 to the power of +2, which is 1/4. 2 to the power of -1 is 1 over 2 to the power of +1, so 1/2. 2 to the power of 0 is 1, and 2 to the power of 1 is 2. All right, so -2, comma, 1/4, -1, 1/2, 0, 1, 1, comma, 2. Label it, oopsies, label it f of x. Okay, and then we flip-flop these, so this becomes 1/4, comma, -2, 1/2, comma, -1, 1, comma, 0, 2, comma, 1. So 1/4, -2, 1/2, -1, 1, 0, 2, comma, 1. Okay, so logarithmic and exponential functions are always going to look something like this format, okay? So today's homework is actually a packet or worksheet. It's the 5.2.1 independent practice. So it looks like this. It has 3 pages, so this first page, second page, third page. So some of this is a review or tiny review of stuff that we learned last class for 5.1. So like this first page, determining whether the function is 1-to-1, using the horizontal line test, finding the inverse and stating its domain and range, verifying that two functions are inverses of each other, graphing the 1-to-1 function and drawing the graph of the inverse, etc. Okay, and then in the next couple pages, we're gonna get to these similar types of problems where you're having to sketch the exponential graph and then its inverse, the logarithm. Okay, so please go ahead and get working on this. If you do not have a printer at home, that is totally fine. You can just write the questions on a separate sheet of paper and then ask if you have any questions.